So it's 2 o'clock, and welcome everyone to the last day of our mini school, which was looking at introduction to quantum thermodynamics, specifically looking at open systems. And I would like to thank Dr. Graeme Pleasance for giving the lectures and hosting this mini school. And I hope everyone gained or benefited a lot from this. And who knows, you might have sparked some new research interests in the process. So, but you guys are not here to listen to me. So Dr. Graeme, again, thank you very much for taking time off your busy schedule, I assume, and giving those lectures on the mini school. So over to you, and thank you everyone again for sticking till the end of the last lecture.
Okay, thank you, Tutukile. Let me just share my screen. So you can see, just to confirm that you can see my slides, okay, and you can see the changing.
Yes, I can see them.
Okay, okay, fantastic. Okay, thank you. Yes, thank you, Tutukile, again for that, for the introduction. So hi everyone, and welcome back again to the final lecture in this mini school series. So I just realized that on the first slide, in fact, there's a slight typo, so this should be the 28th of February, obviously. So yes, so let me just get straight into things. Okay, so just to kind of briefly outline what we've looked at so far in this mini school. So in the first lecture, I gave a kind of general motivation for why we're interested in studying quantum thermodynamics, as in particular an extension of ideas that we deal with in macroscopic thermodynamics, so ideas pertaining to things like work and heat, and how we can generalize this to deal to microscopic quantum systems. Okay, and so what we did was we just kind of reviewed some of the statistical foundations of quantum mechanics. We introduced the idea of open quantum systems and looked at some of the theoretical tools that we can use to describe open quantum system dynamics. So in particular, we introduced the idea of the time evolution of open quantum systems as being described in terms of completely positive and trace preserving maps, or CPTP maps. Okay, and then we looked at Markovian master equations, or introduced Markovian master equations as belonging to particular class of these CPTP maps, so those that obey a so-called dynamical semigroup condition. And so the GKSL form of the Markovian master equation is essentially the differential form of the CPTP maps that belong to the dynamical semigroup. Okay, and then we looked at how we can, starting from a microscopic model of a quantum system that interacts with a thermal reservoir, we looked at how we can derive these types of Markovian master equations in practice under a set of assumptions. So in particular, the recoupling assumption and separation of timescales. Okay, and so in this kind of Markovian master equation framework, we looked at how we can derive the first and second laws of thermodynamics. So the first law being about energy conservation, the second law being about irreversibility, so a non-negative total entropy production. Okay, and what we kind of at least towards the end of the last week's lecture, we looked at how we can apply these this framework to analyzing quantum thermal machines, so both continuously driven thermal machines and also reciprocating machines. So in this week's lecture, what I'll do is, because we didn't really go over this in much detail, I think most of this week's lecture will be devoted to going over this content. Okay, so originally I was planning also addressing how we can at least one or two approaches of how we can generalize the Markovian master equation framework, which only applies a weak system reservoir coupling to the case where we have strong interactions. So I do have a little bit of material that in this lecture, but I'm not sure what the likelihood is that we'll get to that. So just to kind of warn in advance, I might not cover this material, but if you're interested, these lecture slides will be uploaded onto the NITheCS website. So if you want to review that content, then you should be able to access it from these slides. Okay, so maybe so a good point to start is to review some of the content that we did last week. That will be important for when we discuss continuous and reciprocating thermal machines in this lecture. Okay, so in last week's lecture, we developed the idea of the first law. So what we did is so the way we did this is that we first considered an isolated system whose Hamiltonian can be written in this form. So this is a system plus reservoir plus some interaction, and we assume that that on our system that we act some kind of time-dependent protocol that's encoded in this parameter that I call lambda here. So in this kind of schematic on the right-hand side, our system in the kind of the framework of macroscopic thermodynamics, the way that we can our system could be something like, for example, a gas, and we have some kind of piston that either can compress our gas or which our gas can expand against. So in this type of setup, this parameter lambda is essentially relates to the control of this piston. Okay, and so this is kind of conceptually conceptualized in kind of macroscopic thermodynamics. So in kind of quantum thermodynamics, what this lambda t might represent is some kind of driving protocol. So that's delivered through something like, for example, like a laser field that's applied to our system. Okay, and so if we start from the case where, because our system plus reservoir is isolated, its internal energy we can assume it to be written as the expectation value of the full system Hamiltonian. Okay, and then under this weak coupling assumption, so in particular the Born approximation. So if you remember, I introduced the Born approximation as this assumption that the total density matrix of our system plus reservoir can be approximately factorized into the reduced system density matrix and the equilibrium state of the reservoir at any time. So applying this kind of weak coupling approximation, we can approximate the total internal energy of our isolated system as just the bulk contributions from the system itself and the reservoir. Okay, and so what this allows us to do is to kind of consistently identify the internal energy of our open system as just the expectation value of the local system Hamiltonian HS. Okay, and so from this definition of the internal energy of just this system, so in this case what's contained in this like yellow block here, we can derive the first law. So what the first law tells us is that any change in internal energy can be partitioned into work and heat contributions. Or equivalently, we can say that we can write this in differential form. So we can say that the time derivative of the internal energy of our system can be represented as power, which is the time derivative of the work, plus any corresponding heat currents, which are the time derivative of the heat component. Okay. So so in last week's lecture, I kind of I only looked at the case where our system interacts with a single thermal reservoir, so what's schematically depicted here. But you can in fact generalize this to a situation where your system interacts not just with one reservoir that's initially in thermal equilibrium, but potentially multiple reservoirs, independent reservoirs that are in equilibrium at their own respective inverse temperatures, beta J. Okay, and so if we now just kind of consider this slightly more general case, what we can do is formulate the first law. So what we do is just take the time derivative of our internal energy. And so if you just straightforwardly apply the product rule, we have this first term, which we can identify as the power of our system, so the time derivative of the work, plus this second contribution, or the sum of, or the second contribution, which is written as a sum of the corresponding heat currents. Okay, so what this second term in this multiple reservoir situation, what this second term describes is the heat currents that flow from our system into each of the corresponding reservoirs, which I label here by this index J. Okay, and just to just to recall here, so we're assuming here that our reduced system obeys a Markovian master equation that's written in this form. Okay, so just the thing to point out here is that I've introduced this so just to say from last time, we have this Liouvillean operator L, which I also called the generator of our master equation. Okay, and so what we can also do is introduce this new super operator, which here I use calligraphic D to represent. And so this is super operator is sometimes referred to as the dissipator of this master equation. Okay, and so what each of these dissipator super operators describe is the dissipative effect of each of these reservoirs on our system. Okay, and so if you can recall, we looked at the example of a two-level system interacting with a thermal reservoir in last week's lecture, and what this term described was the possible thermal emission and absorption of photons from the reservoir. Okay, so you can think of each of these terms describing similar dissipative effects from each of these thermal reservoirs indexed by J. Okay, and so also just a note here is that our system Hamiltonian in this master equation is time dependent, so it depends on this driving protocol, which is characterized by this lambda. And so I've put this kind of star here next to the equation to basically imply that this master equation is technically only valid under the additional assumption that we assume that this driving or the system is driven much more slowly relative to the timescales over which its free dynamics occurs, and also the timescales describing its relaxation under the effects of each of the reservoirs. Okay, so basically this is valid within the range of the adiabatic theorem. Okay, so just to kind of say that we assume a slow driving on our system. Okay, and so as I said, so this first term we identify as the power, which is just the time derivative of work. Okay, and so this is just this term can be calculated purely in terms of or it is calculated as the expectation value of the time derivative of just our system Hamiltonian, so not the time derivative of everything contained in the trace. Okay, and then the second term is just the sum of the heat currents going from our system into each of the reservoirs. Okay, and so that's denoted here by this calligraphic I. So I here represents a heat current. Okay, so that's how we can derive the first law within this Markovian master equation framework. So what we also did was look at the second law, which introduces the idea of thermodynamic entropy and irreversibility. So the starting point for deriving the second law is to utilize our definition of these heat currents. Okay, and so in last week's lecture, when our system only interacted with a single thermal reservoir, we looked at the relative entropy and showed that the relative entropy of our reduced system density matrix against the corresponding thermal Gibbs state is generally non-negative, and we can identify the negative of its time derivative as the entropy reduction rate. So we can do a similar thing here in the multiple reservoir case. Okay, but this time what we do is we start from the von Neumann entropy of the system. Okay, so this is defined in this way, and what we do here is we identify this as the thermodynamic entropy. Okay, and to start with, we take its time derivative. So one can show that the time derivative of the von Neumann entropy can be written in terms of each of the dissipators of our reservoirs in this way. And so how you can show this explicitly is by using the spectral decomposition of the reduced system density matrix. Okay, so equivalently, you can write this von Neumann entropy as the sum over the negative of the ith eigenvalue times by the log of the ith eigenvalue. Okay, so using this kind of spectral decomposition, you can derive this expression. Okay, and so how we then get to the second law. So if you can recall, the second law essentially states that the entropy reduction rate, so the time derivative of what here I call sigma s. So sigma s here is the entropy reduction. Its time derivative is the entropy reduction rate. What the second law says is that this is non-negative. Okay, and so how we can show this within this framework is we can subtract from the time derivative of the von Neumann entropy this quantity. Okay, so this is the inverse temperatures of each of the thermal reservoirs multiplied by the corresponding heat current. And so this can be written in this form. So so this just comes from this definition of the heat current up here. So this log here, it's relatively straightforward to see that if you just you can expand out this expression just to get what's on the right hand side here. So what we can then do is equivalently write this in terms of what we call here a time dependent Gibbs state. So if you can remember from previous lectures, the Gibbs state is essentially just the canonical ensemble. Okay, so basically it's the corresponding thermal equilibrium state of our system, and it's defined with respect to its local Hamiltonian, so H of S. In this case, though, we're now dealing with a time-dependent system Hamiltonian. So in fact, what I define here as the Gibbs state now is time-dependent, and similarly, its corresponding partition function is also time-dependent. Okay, and so we can write the left-hand side here in this way, and what we can then do, so the reason we want to write it in this form is then we can utilize what's called Spons inequality. So this is what I also used in last week's lecture in the derivation of the second law. And so what Spons inequality tells us is that that this quantity here is generally non-negative. Okay, under the assumption that this state, this time-dependent Gibbs state, satisfies this relation. So in other words, it's a steady state, it's an instantaneous steady state of our Markovian master equation at any time t. Okay, and so if this is the case, then we can show that we can then show that we can rewrite this basically in this format, and we can then just apply this inequality to show that this this expression is non-negative. Okay, and so if we then identify this quantity as our entropy production rate, we then recover the second law. Okay, and so this is derived in a slightly different way to what we did last time. So just to clarify here, this version of the second law applies to the case where our system interacts with potentially multiple thermal reservoirs, each at their own inverse bath temperature or inverse temperature, under the assumption that this relationship holds. Okay, and so in last week's lecture we did this, but just for the single reservoir case. Okay, so that's the first and the second law. So hopefully that's reasonably clear. So what we can now do is we can use these definitions of the first and second law to analyze thermal machines, so in particular heat engines and refrigerators. So for the remainder of today's lecture, what we'll do is we'll look at two particular examples of quantum thermal machines. So these are categorized as either continuous machines or reciprocating machines. So I'll define what these are in the following. And what we'll also do is then look at how we can, so a particular example of a reciprocating machine is what's called a quantum, or is built on what's called a quantum Otto cycle. So we'll look at an example of a quantum Otto cycle as well. And time pending, although I expect we probably won't have enough time, but assuming that we do, then I've also included a couple of slides on how on possible ways in which you can generalize some of these concepts that we looked at so far to dealing with strong system reservoir coupling. Okay, so as I mentioned, there are generally kind of two classes of quantum thermal machines that are that we can consider. So these are represented as either continuous thermal machines or reciprocating thermal machines. So we'll first look at the case of continuous thermal machines. So these are basically these are thermal machines that so the way they operate is that we have what we call a working medium. Okay, so this is basically just some quantum system that in this schematic on the right side I label Q, and this working medium continuously couples to both a heat source and a heat sink. Okay, so in this schematic on the right side, we have our working medium, and it can exchange heat with a hot reservoir and exchange heat with a cold reservoir, and we generally apply some or the system can either or the operation of this machine is either driven by the input of some work or simultaneously the extraction of some work. Okay, so the working medium of the engine is essentially the component of the machine through which work extraction or injection occurs. Okay, and so one such example of a continuous thermal machine is one which is outlined in this paper, which in fact goes all the way back to 1959. So some people cite this paper as being the first example of a quantum heat engine that was considered in the literature. And so what the authors here did was they looked at how you can visualize a maser as effectively a quantum heat engine. So what you have is you have both a heat sink, a heat source and a heat sink, so a hot and a cold reservoir. And the way that this setup can be visualized as a heat engine in the sense that that the population so we have a 3-level system as our working medium, and the population inversion that occurs in our 3-level system essentially drives a heat current from the hot reservoir to the cold reservoir. Okay, and so you can this basically describes the operation of a maser. So in that way, you can visualize a maser as a quantum heat engine. Okay, although just in this example, I should clarify that it's analyzed in the framework of a quantum heat engine, although it's not really a quantum heat engine in the sense that the system that they consider in this setup doesn't doesn't exhibit any kind of non-trivial quantum features like entanglement or coherence. Okay, but this is kind of cited as one of the first examples in the literature of the analysis of a quantum heat engine. Okay, so in this kind of setup that we have here, the dynamics of the working medium is described by this master equation. Okay, so this is just the same as the Markovian master equation that I gave in the derivation of the first law. And here we have the dissipators for each of our reservoirs. And so this here we only have 2 reservoirs, a hot and a cold one. Okay, so this J index labels both the hot and the cold reservoir. And so here we have some adiabatic driving that's also applied to our system. And in this kind of continuous engine, we assume that this is periodic in the sense that this relationship holds. Okay. And so for continuous thermal machines, we can kind of further categorize these as either driven machines or autonomous machines. Okay, so in the case where we have some external protocol that's applied to our working medium, that's generally periodic protocol, this is naturally a driven continuous machine. So this, as I said, corresponds to the case where we have some kind of external control that mediates the extraction or injection and extraction of work from our system. Okay, so this is the example that we'll consider in this lecture. So I won't go over the second example of continuous thermal machines, but these are categorized as what are called autonomous machines. So these are ones where you don't have a kind of explicit time-dependent protocol that is applied to our working medium, but you have an additional reservoir which effectively or has the same or a similar effect as the driving protocol. Okay, so in other words, our external drive is replaced by what's called a work reservoir. Okay, so I won't, due to the kind of time constraints, I won't consider these types of machines in this lecture. But an example of such an autonomous thermal machine is what's called a quantum absorption refrigerator. So that's looked at in this paper here. So an absorption refrigerator is the case where you have three reservoirs. So you have a hot, cold reservoir and an additional work reservoir. And then in this case, what happens is that this work reservoir acts to remove excitations from the cold reservoir and creates an additional excitation in the work reservoir plus another excitation in itself, so in also the work reservoir. Okay. So what we'll do is now we'll look at we'll look at a particular example of a continuous heat thermal machine, so one which acts as a heat engine. Okay. So okay, let me just say before we do that, actually, so in the case where we're dealing with a driven thermal machine, okay, we have this time-dependent external control that is applied to our working medium, and we assume that this drive protocol is periodic, okay, where this capital T is the periodicity of our control parameter. Okay, so here, as I kind of already mentioned, we're assuming that this master equation is technically only valid under the assumption that this driving is implemented adiabatically. So generally, it's performed much slower, or the timescale relating to this drive is much larger than the timescales relating to either the free dynamics or the relaxation dynamics. Okay, so I just wanted to also point out here is that it's possible to drive Markovian master equations which also apply to non-adiabatic drives that are also periodic. So ones in which the system Hamiltonian satisfies this condition, and so this can be done under what's called the Floquet formalism. Just again for simplicity, I won't go over that here. I'll just assume that we're dealing with an adiabatic drive. But if you're interested, then I would recommend looking at the sorry, my laptop just fell down. Okay, yeah, if you're interested, then I recommend looking at this textbook of Heinz Peter Breuer and Francesco Precioccioni. So there's a chapter in this book that's dedicated to, or at least a section in a chapter of this book that's dedicated to deriving Markovian master equations using the so-called Floquet formalism. Okay, and so an important aspect of these continuous thermal machines is that they are generally operated out of equilibrium. Okay, so they are working medium. So our working medium interacts with both the hot and the cold reservoir, and generally it will enter after a sufficiently long time. Our working medium will enter a periodic steady state. So this is defined in the following way. So what happens is that after a sufficient time, our system will reach some steady state, which basically oscillates periodically at the same period as the drive frequency. Okay. Okay, and so how can we analyze these types of machines using the weak coupling derivations of the first and second law I gave previously? So we can do this in the following way. So if we now look at one particular example of this continuous thermal machine, so in the case where it operates as a heat engine. So a heat engine is one in which we have a heat current that flows from our hot reservoir to the cold reservoir, and generally what our time-dependent external drive does is extract work from our working medium. Okay, so generally, this is kind of summarized on the right hand side. So for a heat engine, the heat current from our hot reservoir is positive. The heat current from our into our cold reservoir is negative, and the corresponding power output of our working medium is also positive. Okay, so so essentially, yeah, this is the definition of a heat engine. So here, just to note that what I call P out, so this is the output power, and just to be clear, this a minus sign is included on here because so previously, when we looked at maybe I can just quickly go back to the previous slide. So so here, when I write down the power, okay, this represents the power that's done, that's applied to our system. Okay, so in other words, this corresponds to a case where our drive is increasing the internal energy of our system. And so the reason here where I include this minus sign is the fact that this now represents the output power. Okay, so essentially, if this quantity is positive, then this corresponds to a net amount of energy that's extracted from our system, which is what we want for a heat engine, right? Okay, so our starting point for analyzing this is to look at the internal energy of our working medium in the steady state. And so from the definition of the internal energy that I gave before, this is just the expectation value of our system Hamiltonian. Okay, and so this superscript SS here is just a reference the fact that this is we're looking at the steady state. Okay, and what we can do is we can rewrite this in a slightly different form. So what we can do is rewrite the terms that are contained in this trace in a rotating frame that rotates at our drive frequency. Okay, so I've skipped some of the technical details here, but this can be done through essentially applying a unitary transformation to the local system Hamiltonian and also the reduced system density matrix here. And by doing so, you can show that this quantity satisfies this equality. Okay, so in this rotating frame, so these tildes here indicate that each of these quantities are defined in this rotating frame. And because this is defined to oscillate at the periodicity of our drive, the steady state in this rotating frame is time independent. Okay, so this just comes from the periodicity. So if I just go back, this just comes from the fact that in the steady state, the reduced system density matrix is periodic with respect to this drive. Okay, so in this rotating frame, this becomes time independent, and similarly, our system Hamiltonian that contains the driving protocol also becomes time independent. Okay, and so if we take the time derivative of this, we can just then use the fact that this is now time independent to show that in the steady state there's no net change in internal energy of our system. Okay, and so from the first law, what that now implies is that we can write down the following relation. So so this is just the statement of the first law that I gave previously, but just again clarify here that I've introduced this minus sign because now this so previously the P represented the work, the power performed on the system. Now this represents the power extracted from the system. Okay, and so if you do that, it's straightforward to show that you can just write down the output, or the output power in the steady state satisfies this relation, and we want this to be greater than 0. Okay, and so this comes from the first law. So this is essentially just a statement of energy conservation in the steady state. We can now apply the second law to understand I mean, due to the fact that this engine operates out of equilibrium, then it's generally going to be operated irreversibly, right? And so this is kind of captured through the application of the second law. So the second law is so this is just what I gave on the previous slides, and you can then use the fact here is that in this steady state, you can use the fact that the von Neumann entropy. So if we also transform the reduced system state in the von Neumann entropy to the same rotating frame up here, we can use the fact that the von Neumann entropy is invariant under unitary transformations. And then we can also use, again, the fact that this steady state in this rotating frame is also time independent to show that, well, this first term, if we then take the time derivative of this, because this is time independent, it just vanishes. And then what this implies from the second law is that we have this inequality between the heat currents relating to the heat flow from the working medium to the cold reservoir and the hot reservoir to the working medium. Okay. And then, so once we've done this with the second law, we can look at the efficiency of our engine. Okay. And so for a heat engine, the corresponding efficiency is defined as the output power of our engine divided by the heat current from the hot reservoir to our working medium. Okay, so intuitively, this just represents the proportion of energy. So if you think it here, like energy is absorbed from the hot reservoir by our system, and some of it's going to be extracted out by this dry protocol, and some of it's going to go to the cold reservoir. So what this does is it represents the proportion of energy that's extracted that comes from the hot reservoir, okay, per unit time. And so just using the essentially the first and the second law that we derived, or just using these two quantities that in these boxes that we derived using the first and second law, we can rewrite this in the following way. And generally, you can show that this satisfies this following inequality. So this quantity on the right-hand side, so this 1 minus the ratio of the temperature of the cold reservoir to the hot reservoir, is sometimes what's called the Carnot efficiency, okay? So what the Carnot efficiency represents is the maximum possible efficiency at which a heat engine can operate. And so if any of you are familiar with kind of macroscopic classical thermodynamics, the Carnot engine or a Carnot cycle is an example of a thermodynamic cycle that operates irreversibly and is able to achieve the maximum possible efficiency that's dictated by the second law. So what this basically shows us here is that the efficiency of our continuously driven engine can never exceed the efficiency of the Carnot engine or the equivalent Carnot cycle, which shows consistency with macroscopic thermodynamics. Okay, so that's kind of, yeah, as I said, what we would expect from kind of standard macroscopic thermodynamics. Okay, and so that was a heat engine. So we have some drive protocol that extracts work from our system. So we can also consider another, well, the same type of continuously driven machine, but now one which operates in reverse. So this is what's called a refrigerator. So a refrigerator is a machine which extracts energy from our cold reservoir and deposits it into the hot reservoir, and this requires the input of some work into our working medium here. Okay, so essentially this is just the same as previous, but now what we want is the output power to be, we want a net input of work per unit time into our working medium to drive this heat current from the hot to the cold reservoir, right? So this is just the opposite to what we had on the previous slide, and so we can just look at that. We can apply the same. We can apply the first and the second law in the same way to what we did previously to analyze this kind of continuously driven refrigerator. Okay, and so here this is the first law. So this is the same as the first law that I gave on the first couple of slides. So here, just again to emphasize this, P in represents the input power into our system. Okay, and so this is the negative of the output power. And so what we can derive is a similar relation, just applying the first law and the fact that in the steady state, in the periodic steady state, the time derivative of our internal energy is 0. We can then derive this relation, and then again looking at the second law, similar to what we did with the heat engine, we can just come up with the same inequality as we did previously. Okay, and so so for a refrigerator, the corresponding figure of merit isn't the or the relevant figure of merit isn't the efficiency. So it's what's called, instead the coefficient of performance. Okay, so this is kind of a quantity that analogously measures the efficiency of our refrigerator. And this coefficient of performance is defined as the ratio of the cold reservoir heat current divided by the input power. Okay, so in an analogous way to the efficiency for the heat engine, what this represents is the ratio of the, how much power we need to input to drive a particular heat current from our cold reservoir to the hot reservoir. Okay, and so what we can do is apply the second law again to rewrite this expression here in this form. So in terms of the ratio of the heat current from the heat current for the hot reservoir of the cold reservoir, and what one can do is show that it satisfies this inequality. Okay, and this quantity here, which depends on the temperature of the cold and the hot reservoirs, is what's called the Carnot coefficient of performance. Okay, so this represents, similar to what the Carnot efficiency that we had on the previous slide, this represents the maximum possible efficiency that a refrigerator, or the maximum coefficient of performance that a refrigerator is able to perform at with a, and this only occurs in the case where the machine is operated reversibly. So here, our driven engine can never, or at least in practice, can never actually satisfy this bound due to the fact that it generally operates out of equilibrium, and so therefore its efficiency is going to fall below the coefficient of the Carnot coefficients of performance. Okay, so that was the continuously driven case, and looking specifically at heat reservoirs and refrigerators. So now we can move on to a slightly different class of engines, which are called thermal machines that are called reciprocating thermal machines. So these are, so in contrast to the continuous case, these are ones which, in which the work and the heat extraction isn't implemented continuously, but which occur over a discrete sequence of operations. Okay, and these sequence of operations are called strokes. So this is in the language of kind of macroscopic thermodynamics. Okay, so an example of a reciprocating thermal machine is illustrated on the right-hand side here. So this, in fact, so this phase diagram here, if you want to call it that, represents what's called a quantum Otto cycle. Okay, in particular, a quantum Otto cycle that operates as a heat engine. Okay, and so what a quantum Otto cycle is essentially a four-stroke. It's a four-stroke cycle. So here we have a sequence of 4 different operations, which are labeled here 1, 2, 3, 4. Okay, and so in this kind of diagram, on the x-axis we have our driving, or like our driving parameter. So this just represents the magnitude of this driving parameter at a particular time, and on the y-axis we have the internal energy of our system. So in this quantum Otto cycle, we have it consists of 4 strokes, and these correspond to strokes in which either work is either extracted or injected into our system. So that occurs during the stroke here that goes from 1 to 2 in this diagram, and also similarly that goes from 3 to 4 in this diagram. Okay, and then we have 2 other strokes that go from 2 to 3 and 4 to 1 that represent the or are strokes in which our working medium is attached to either a hot reservoir or a cold reservoir. Okay, and then as you might imagine, there's generally some exchange of heat between the two during each of these strokes. Okay, and so yes, so this this quantum Otto cycle is quite at least in terms of quantum thermodynamics, is one of the most popular models of reciprocating thermal machines that have been analyzed in the literature. And so I'll mention maybe the reason why that is, but if you can recall, firstly, just from the first lecture, I gave 2 examples of experiments that have recently been done, which effectively implemented these four-stroke quantum Otto cycles. Okay, and so that's an example of a single atom heat engine that was implemented using trapped ions. Okay, and so that was that. In this case, a single ion was used as the working medium of a four-stroke Otto cycle. And then there was also this other implementation that was done using nitro vacancy centers in diamond. Okay, so if you're interested in looking at some experimental examples of these quantum Otto cycles, then these two papers are probably the most well-known experimental examples. Okay. And so just to mention that there are also other examples of reciprocating heat engines. So there's another one which is also known as the Carnot cycle, so which I mentioned. So this is a particular example of a thermodynamic cycle that is operated reversibly. Okay, and so these are generally less popular to analyze in the literature, but just due to the fact that they tend to be much harder to analyze using this Markovian master equation framework, and that's due to the fact that for Carnot cycles, the work extraction or injection into the system and also the heat exchange between the reservoirs occurs simultaneously in each of the strokes, whereas for the quantum Otto cycle, the work extraction / injection and heat exchange occur separately in the different strokes. Okay, so in this right-hand side diagram, so in the first stroke here, so going from 1 to 2, the work is only either extracted or injected into our system. Okay, so there's no heat exchange between the working medium and any of the reservoirs. In the second stroke, we only have heat exchange, so no work is either injected or extracted here. And similarly, in this third stroke, we only have, again, work exchange. So that's just to kind of mention that these Otto cycles tend to be a little bit easier to analyze, and that's why most papers in the literature are dedicated towards analyzing these types of cycles. Okay, and so just another thing to mention about these cycles is that when we analyze them, we generally they're typically analyzed under this assumption of adiabaticity of the drive protocol. Okay, so I mentioned on the previous slides that the Markovian master equation that we're using, so we just assumed that we could just attach the driving protocol to our system Hamiltonian, and that it doesn't affect our Markovian master equation in any way. And so generally we can only do this under the assumption that our driving is adiabatic. Okay, and so what that kind of implies for the operation of this cycle, okay, is that each of the two strokes in which we inject or extract work from our system, these, if we want to actually perform these adiabatically, these have to be performed in principle infinitely slowly. Okay, and that's to prevent basically the buildup of coherence in the energy eigenbasis of our system Hamiltonian. Okay, so so why is that important? So why is this adiabaticity important for the operation of the cycle? And I mean, the reason for that is because if we don't operate the work exchange strokes adiabatically, so under this condition, then what happens is that our system can gain. So if you look at the reduced density matrix of our system, if these strokes are not performed adiabatically, what happens is that we get coherences that are generated in the energy eigenbasis of our system Hamiltonian, and that's a problem because generally what you can show is that this lowers the performance of the engine. So in other words, we have to inject extra work into the cycle in order to mitigate the appearance of these coherences when these strokes are not performed adiabatically. Okay. And so in practice, this then lowers the efficiency of our engine. And so I just wanted to kind of mention that in the literature, there are some powerful techniques that have been introduced to try to mitigate this kind of drop in efficiency due to operating outside the adiabatic regime. And these are what are called shortcuts to adiabaticity, okay? And so what these are a class of methods that look at implementing drive protocols in our cycle that that allows us to do two things. So it allows us to firstly perform each of the work injection and extraction strokes in such a way that at the beginning and end of the stroke, that our system remains diagonal in the energy eigenbase of our system Hamiltonian, but at the same time allows us to perform each of these strokes in finite time. Okay, so there's an extensive amount of work that's been done in the literature on these so-called shortcuts to adiabaticity, so I won't go into this, but if you're interested, then there's this paper contains details on some of these techniques. Okay, so for the remaining 10 minutes or so, what I'll do is look at a particular example of this quantum Otto cycle. So in particular, a quantum Otto cycle that operates as a heat engine. Okay, and so so within the Markovian master equation framework, this cycle or the time evolution of our working medium around this cycle can be described in terms of these, in terms of the composition of 4 CP-TP maps. Okay, so here, just to remember, this phi represents a CP-TP map, and this we assume that each of these strokes in our cycle is implemented in a certain finite amount of time. So here, this is labeled. So the stroke going from 1 to 2 occurs in time t1, from 2 to 3 in th, from 3 to 4 t2, and from 4 to 1 in tc. Okay, so generally, because this represents a closed thermodynamic cycle in the sense that our system is initialized, our working medium is initialized in a state at this point in the cycle. Once we complete each of these 4 operations, we return back to the same state again. Okay, and then the cycle repeats. Okay, and so a single repetition of this cycle, or the time evolution of our working medium in a single repetition of the cycle, will be represented by this this dynamical map, right? And because it if we assume each of these belong to a dynamical semigroup, then by construction this map phi Otto represents a CP-TP map. Okay, so it basically represents a physical evolution of our system or working medium. Okay, so in the example of a heat engine, what we have are 4 strokes. Okay, and so as I mentioned, we have 2 strokes in which we only have work injection or extraction from our working medium, and then we have 2 other strokes in which our system, our working medium, is attached to either a hot reservoir or a cold reservoir. Okay, and so what we can do is again just apply the first law that we introduced previously to analyze the work that is either injected or extracted from our system in these 2 strokes, and simultaneously the heat that flows into our system or out of our system when it's attached to either the hot or the cold reservoir. Okay, and so so just to say as well that these 2 strokes which occur without any heat exchange, these are also what are called isoentropic strokes. And so isoentropic here means that the entropy of our system during each of these strokes remains constant. Okay, and so that's the case because this work extraction or input is described by, it corresponds to a unitary operation, and by definition unitary operations don't change the von Neumann entropy of our system. So these are isoentropic strokes, whilst the other ones are called isochoric strokes. Okay, so this is just language that's also used in classical thermodynamics for Otto cycles. So this language is just adopted from classical thermodynamics. So the isochoric strokes are the ones where the system interacts with either the hot or the cold reservoir. Okay, so if we just now look at the application of the first law to look at to determine expressions for our work input and extraction. So here we call these W1 and W3. So our first stroke is what's called a compression stroke. So this is one in which we our system is initialized in some state, which here is the thermal, so it's the Gibbs state at the inverse temperature of the cold reservoir, okay? And then what we do is we increase this driving parameter lambda from a value lambda1 to lambda2, where we assume that lambda2 is generally larger than lambda1, okay? So that's kind of represented here in this diagram. So here we're increasing lambda as we go from left to right. And so we can just calculate the work that's injected. So in this stroke, in the compression stroke, work is injected into our system. So its internal energy increases, okay? And so we can calculate that work. So just from the first law, because obviously there's no heat exchange, the change in internal energy is just due to work, okay? And so this just comes from the definition of work that I gave previously. So this just, again, this is just the change in internal energy of our system due to the change in the control parameter lambda, okay? So this is an expression that we get for the work that's input during this first isoentropic stroke, okay? And so in the next stroke, so what we call the hot icicle, so our system is attached to the hot reservoir and exchanges, so there's some exchange of energy, and then what happens is that we assume that our working medium thermalizes with respect to the hot reservoir, okay? And so what I mean by this is that our system, if we assume that this TH is sufficiently large such that our system approaches or reaches equilibrium, where its state, so in this weak coupling framework, we noted that the stationary or the steady state of our Marshall equation under certain conditions is just the thermal Gibbs state at the reservoir temperature, okay? So here we apply that, and so we can say that at this 0.3 here, our working medium will be in a thermal state at the hot reservoir temperature. So that's just how we obtain this expression for the heat. So again, this is just because there's no work input during the stroke, it's just given by the change in the internal energy. And because our system Hamiltonian doesn't change, this is just due to the change in the state of the change in internal energy comes from the change in the state of our system, okay? So at this point, our working medium is equilibrated with the hot reservoir. What we then do is perform the second isoentropic stroke. So this is what's called an expansion stroke. So this is one where work is extracted from our system, okay? So this corresponds to when so it's essentially the inverse of this stroke. So rather than increasing this control parameter, we decrease this control parameter. So we go from lambda2 back to lambda1. Okay, so again, just applying the first law in the same way as we did for the compression stroke, we get this expression for the work extraction. And then the last stroke of our cycle is just the cold icicle. So this is equivalent to the hot icicle, but now our system is interacting with a reservoir at a lower temperature, okay, than the hot reservoir, obviously. And so again, the heat exchange between our working medium and reservoir is just calculated from the change in internal energy, which is just down to the change in the corresponding state, okay? And so because our cycle is thermodynamically closed, so we always, if we go around any integer number of cycles, we always end up in the state that we begin with, okay? And because the internal energy is a state function, this implies that there's no net change internal energy of our system when we go around this cycle, okay? And so what this implies from the first law is that that the sum of all of these contributions is 0, okay? And so what we can do is kind of make things a little bit more explicit. So just in the last couple of minutes of this lecture, what we can do is apply this to an example where our working medium is a two-level system. So this corresponds to the case where our system Hamiltonian can be written in this form, okay? So here, this I is just the identity matrix, and this sigma z is the Pauli Z operator, okay? And so here, what our time-dependent control parameter does is it basically changes the energy splitting of our two-level system during each of the isoentropic strokes. So in the compression stroke, what happens is that if you think of each of my hands as representing the two energy levels of our system, in the compression stroke, what happens is that this dry protocol increases the energy gap. So what happens is that our upper energy level goes like this, so the energy gap increases in this stroke, and then what happens during the expansion stroke is the reverse. So our system starts like this at 0.3, and then as we decrease lambda, it decreases the energy splitting between our ground and excited state. Okay, and so for this particular example, you can come up with explicit expressions for the work and the heat from each of the strokes. Okay, and so this is maybe something that you can do yourself, so I won't go over the details. So you can just verify that these are all the expressions that you get for the work input, the work extraction, and also the heat exchange between the hot and the cold reservoirs. Okay, and so what you can do, like we did with the continuous driven heat engine, we can define an equivalent figure of merit for the cycle, which is its efficiency. So again, this is just the ratio of the heat, so the ratio of the work output of our cycle divided by the ratio of the work output of our cycle with respect to the heat that is absorbed during this hot icicle. Okay, and so this definition is just analogous to the one that we use for the continuous heat engine. Okay, and so what you can show is that if we just substitute in here W1 and W3 into this expression, and also the total heat that's absorbed by our system in the hot icicle, then we can show that we just get this expression for the efficiency. So it's just 1 minus the ratio of the frequency of the energy difference between the excited and ground states of our system during the compression stroke and the expansion stroke. Okay, and so what one can also generally show is that, like with the continuous heat engine, is that this is always upper bounded by the Carnot efficiency. Okay, and so this again shows a kind of consistency with macroscopic thermodynamics, that we can't basically beat, we can't operate our engine more efficiently than what we can in the case where we have where our engine can be operated reversibly. Okay, so I think that I've pretty much got to the end now, and it's now a few minutes past 3. So like I said, I've included a couple of slides on ways of or approaches that allow you to deal with strong coupling. But I think what I'll do in the interest of time is just say that if you're interested in this material, then these lecture slides should be uploaded to the NITheCS website. So if you want to take a look at this material, then you can access it. You can access it there. So so apologies for that. I didn't anticipate how long it would take to get through the material on the Markovian master equations, and also on the thermal machines. I thought I'd have enough to devote a whole lecture to it, but unfortunately not. Okay, so let me just sum up by saying that so in this lecture, what we have done is looked at so within the Markovian master equation framework, how we can analyze continuous and reciprocating thermal machines. Okay, so what we did is we looked at the example of a heat engine refrigerator in the driven case, and we also looked at an example of a quantum Otto cycle in the case of a reciprocating thermal machine. So we looked at how we can calculate certain figures of merit, so like the efficiency and the coefficient of performance for the driven heat engine and refrigerator. So as I said, we also analyzed this quantum Otto cycle. Okay, coming up with in the case of the 2-level system, coming up with an expression for the efficiency, which is just given in terms of the ratio of the energy splittings during the isoentropic strokes. And then something that I didn't have time to do, but if you're interested, you can take a look at the material that's the lecture slides that will be uploaded onto the NITheCS events page. So I just should say that there are ways of generalizing these weak or extending these weak coupling approaches to dealing with cases where you have strong system reservoir interactions, although this is an area of work that's quite topical at the moment, and there's varying different frameworks that people use and apply to be able to treat strongly interacting systems. Okay, so so apologies for going slightly over time. So let me just end by saying thank you, and yeah, maybe we can see if there's any questions.
Thank you, Graeme. In the Q&A, I don't see any questions, and also in the chat. So maybe we can wait whilst people are still formulating questions.
Yeah, if maybe we can, yeah, just wait a minute or so to see if any questions pop up. If not, then I'm happy to provide my email address similar to what I did last time. So if anybody thinks of questions later on, then please feel free to email me. So I'll just put my email address into the chat.
And yes, you have already mentioned that the recordings, they'll be available on the NITheCS YouTube page, but then also on the website. So
yeah,
they can always
if
go
you go
back.
to the if you go to the NITheCS website and you look under the events page, there should be a link to the YouTube recordings on this event page, and that's where you should also find the corresponding lecture notes for each of the talks there. Okay. Okay, I see a comment from Kovas. Okay, well, thank you. Yeah, thanks. Yeah, also any feedback that you have as well, then please please feel free to forward that on to me. If you have any, if you suggest anything that I could have gone over or maybe would have been more interesting, then also please feel free to send me this feedback. Okay, since we don't have any questions now, then maybe we can.
Yes, I am thinking we can end the meeting. Again, thank you, Graeme, for taking time to give those lectures. And then we have more viewership on the YouTube, even more viewership on YouTube. And I think more people will benefit from them in the long run. So again, thank you so much. And to the attendees, thank you for taking time to attend, because without you attending, we wouldn't have the mini school. So thank you, everyone, and have a good afternoon.
Okay, thank you very much, everyone. Thanks for attending.